In this lecture, I am going to present what is slope deflection equation, what are the assumptions used to develop the slope deflection equations, what are the sign conventions used for the moment, rotational displacement and translational displacement, then derivation of slope deflection equations, application of slope deflection equations, then what are the different steps used for the analysis of continuous beam, then what are the expressions used for finding the fixed end moments for different loading conditions, and what are the equilibrium equations of a continuous beam for different end conditions. First, coming to the introduction, what is slope deflection method? The slope deflection method is a general method by which all beams and rigid frames, whether statically determinate or indeterminate, can be analyzed under the assumption that all deformation is due to the effect of bending moment only. Generally, this method is more preferable for the analysis of statically indeterminate beams and rigid frames. The credit of this method goes to Professor G. A. Manne of the University of Minnesota and published this method in 1915. So in this method, the rotational displacement, that is slope, and the translational displacement, that is deflection, of a rigid joints are taken as the primary unknowns, and their values are determined prior to those of the bending moments or the member ends. So in this method, the moments at the end of a member is first written in terms of the unknown slopes and deflections of the end of joints. Then by considering the joint equilibrium conditions, a set of equations are found, and the solution of this simultaneous equation gives unknown slopes and deflections. Then after knowing the unknown slopes and deflections, the end moments of the individual members are determined. Then coming to what are the assumptions used for the development of slope deflection method. All joints are rigid, that is, the angle between any two members in a joint does not change even after deformation due to loading. Thus at joint A, the angle between the members AB and AC remains theta only even after deformation. So look at this figure. So this is the rigid joint before deformation, and this is the rigid joint after deformation. So this is the angle between the two members. Then after deformation also the angle remains same. Then the distortion due to the axial deformations are neglected. Thus in the frame A, B, C, D, so after distortion, this is the shape A, B dash, C dash and D. So here B to B dash, this is the distortion takes place, and here C to C dash, this is the distortion takes place, and here the axial deformation of the horizontal members are neglected. So what is the distortion takes place at B? The same distortion takes place at joint C, delta amount. Then the third assumption, the shear deformations are neglected. The shear deformations are neglected. These are the three basic assumptions used for the development of the slope deflection method. Then coming to what are the different sign conventions used. So first coming, what are the sign conventions used for the moment? The moment at the end of a member is considered positive when it is in anti-clockwise direction or on a joint in clockwise direction. Similarly, the moment at the end of a member is considered negative when it is in clockwise direction or on a joint in anti-clockwise direction. So this is joint, this is the fixed beam, this is the joint. So here at the joint, this is clockwise, so this is positive. So here at this joint, so this is anti-clockwise, so this is negative moment. Similarly here at joints and end of members. So this is the fixed beam. So this is the moment direction, that is at the end of the members, and this is the moment direction for the joint. So at the end of the members, if anti-clockwise, and at the joints, if clockwise, so this is considered as positive, and if the end of the members clockwise and at the joints anti-clockwise, so this is considered as negative sign convention for the moment. Then coming to what is the sign conventions used for the slope. The slope is positive if the tangent rotates in a clockwise direction. So coming to this figure, and this is the deflected shape. If the slope is a clockwise direction, so that you have to take positive, or the slope is positive if the tangent rotates in a clockwise direction. So this is the tangent, so this tangent is rotate in clockwise direction, so this is positive slope. So here that this is the tangent rotates in anti-clockwise direction with respect to the original axis of the beam. So here this is the negative slope. The slope is negative if the tangent rotates in anti-clockwise direction. And here this is clockwise direction, so this is positive slope. Then what is the sign convention used for the translation displacement? So here you see the displacement of the right hand. This is the left hand and this is the right hand. The displacement of the right hand with respect to the left hand, if downward direction, so this is considered positive. So if the displacement takes place, the right hand displacement with respect to left hand, if downward direction, so that you have to take positive displacement. And this figure, the displacement of the right hand with respect to left hand, if upward direction, will be considered negative displacement. So these are the sign conventions used for the moment, rotational displacement and translational displacement. Then coming to how to derive the slope deflection equations. So let us take a prismatic member AB. The end moments MAB and MBA is calculated by the combination of moments due to the fixed end moments developed by transverse loading on the member and the moments due to the relative displacement of the end of the members and moment caused by the actual rotation of the end of the members. So due to these three effects, the moment can be calculated. Let AB be a member of a rigid structure. So this is member AB of a rigid structure. After loading, it undergoes deformation. This is the deformation takes place after loading. This is the rotational displacement takes place at A, and this is the rotational displacement takes place at B, and this is the translation displacement takes place. So theta A is the rotational displacement at A, theta B is the rotational displacement at B, and the delta is the translation displacement at B. The final moments at the ends A and B are MAB and MBA. So MAB is the final moment at the end A, and MBA is the final moment at the end B. So this is original shape of the beam, and this is the deformed shape of the beam. So here our objective is to derive the relationship between the final end moments and their displacements theta A, theta B and delta. So here we will find out the relation between the final moment and the rotational displacement and translational displacement. So there are different stages to find out the final moment by considering the moment due to the transport loading as fixed end moments, then the moment due to the translation displacement, then the moment due to the rotational displacement. Due to given loading, the end moments MFAB and MFBA developed without any rotation at ends. These moments are similar to the end moments in a fixed beam and hence are called as fixed end moments. These are shown in positive sense in figure 3. What is the external load is given on the beam. First you have to find out what is the fixed end moments. This is MFAB, MFB. This is the positive sense of the fixed end moments. Then due to the translational displacement and without any rotation at ends, the moment developed is 6ci delta by L square. Settlement delta takes place without any rotation at ends. This is similar to the settlement of support in fixed beams. From the analysis of fixed beam, the end moments developed are 6ci delta by L square. So here you see, so this is right hand, this is left hand. So here the right hand with respect to the left hand, if settled in downward direction, so this settlement delta, and due to this settlement, the moment which is developed at the end of the members, that is 6ci delta by L square. This is minus 6ci delta by L square for positive translation displacement. So you have to consider here minus 6ci delta by L square for this downward deflection. So this is the end moments due to the settlements. Then the moment m dash AB comes into play in simply supported beam to cause end rotation theta A1, theta B1 at A and B respectively. So due to this end moment, so this is the rotation takes place theta A1 and theta B1 at the end of the members. Then in figure 6, this is the end rotation due to m dash BA. Similarly here also due to the end moment m dash BA, so here the rotation, end rotation takes place, that is theta A2, theta B2 at the end A and B respectively. The moment m dash AB and m dash BA give final rotation theta A and theta B to the beam AB. To find the rotations due to applied moment m in a beam without end rotation, shown in figure 7, this is the figure. So here the moment is acting at A. So to find out the rotation by considering from the conjugate beam method. The rotations due to the applied moment that can be found out by using the conjugate beam method. So this is the simply supported beam subjected to the end moments m. So here you have to find out what is the rotation at A and at B. So when the moment is acting this side at A, so what is the rotation theta A1 and theta B1. So this you can find out by using the conjugate beam method. So in conjugate beam method, first you have to draw the bending moment diagram, then the m by EI diagram is the loading for the conjugate beam. Then for simply supported beam, so in conjugate beam also you have to consider simply supported condition. Then you have to find out rotation, you have to find out the shear force, and for translation displacement you have to find out the bending moment at that section. So here, So this is the M by I diagram, and here you have to find out by considering that this is the load in conjugate beam. So first you have to find out what is the reaction at both ends. So at when the load is acting this side at 10 day, so this is the loading for the conjugate beam. So here the load is M by IA, and this side the load is 0, and due to this load the reaction at end A is ml by 3A, and the reaction at end B ml by 6A. When the moment is acting at the end A, so due to that moment, so this is the rotation theta A1 and theta B1. Theta A1 is equal to m dash AB L by 3I, and theta B1 is equal to m dash AB L by 6A. Similarly, when the moment is acting at B, this one, when the moment m dash BA is acting at B, so due to this moment, so this is the rotation at A, and this is the rotation at B. So rotation at A is equal to theta A2 is equal to m dash BA L by 6EI, and rotation at B theta B2 is equal to m dash BA L by 3I. So this is the rotation due to the moment which is acting at A and which is acting at B. Finally, so you get the rotation at A and rotation at B due to the rotational moment m dash AB and m dash BA. So the rotational displacement at A, that you can find out by taking theta 1 minus theta 2. So this is the expression. Then the rotational displacement, that is theta B, that you can find out, that is theta B is equal to theta B2 minus theta B1. This is the expression. Then you take 2 theta A plus theta B is equal to, this is the expression, m dash AB L by 2EI. Then from this relation you can find out m dash AB is equal to 2EI by L into 2 theta A plus theta B. This is the rotational moment that you get from the rotational displacement. That is m dash AB is equal to 2EI by L, 2 theta A plus theta B, and m dash BA is equal to 2EI by L, theta A plus 2 theta B. Then after knowing the moments due to the transverse loading, and due to the translation displacement, and due to the rotational displacement, the final moments can be obtained. The final moments MAB is equal to MFAB, and for the positive translation displacement, so you have to take, this is minus 6EI delta by L square. This is due to the, this is the moment due to the translation displacement, and this is the rotational moment m dash AB. So MAB is equal to MFAB minus 6EI delta by L square. Here you got m dash AB is equal to 2EI by L, 2 theta A plus theta B. So just you put here. So MAB is equal to MFAB minus 6EI delta by L square plus 2EI by L, 2 theta A plus theta B. Then after simplification, MAB is equal to MFAB plus 2EI by L, 2 theta A plus theta B minus 3 delta by L. Similarly, the MBA, that you can find out by taking the moment due to transverse loading, and the moment due to the translation displacement, and the moment due to the rotational displacement. So this is MFBA minus 6EI delta by L square, and m dash BA, you know, m dash BA is equal to 2EI by L into 2 theta A plus 2 theta B. M dash BA is equal to 2EI by L theta A plus 2 theta B. So put this value here. Then after simplification, MBA is equal to MFBA plus 2EI by L into theta A plus 2 theta B minus 3 delta by L. So this is the slope deflection equation. Here you got MAB is equal to MFAB plus 2EI by L, 2 theta A plus theta B minus 3 delta by L, and MBA is equal to MFBA plus 2EI by L into theta A plus 2 theta B minus 3 delta by L. So these two are the slope deflection equation. Then coming to the application of slope deflection equation. The rigid joint structures can be analyzed by using the slope deflection equations. the method can be applied to the following structures: continuous beam, and also the method can be used for the frames without side sway and frames with side sway. So you can find out the moment by using this method, and you can apply to the continuous beam and to the frame without side sway and frame with side sway. When the beam supported 3 or more than 3 supports, it is called continuous beam. You know, if there is no side movement of the end of a column in a frame, it is called non-sway. If there is side movement of the end of a column in a frame, is called sway. So you know that is continuous beam, non-sway frame and sway frame. Then what are the different steps used for the analysis of continuous beam? The first step, so you have to determine the piston moments at the end of each span of a continuous beam by assuming each span of the continuous beam as fixed beam. And here you know the sign conventions, that clockwise moments are taken positive and anti-clockwise moments are taken negative. Then by using the slope deflection equations, write all the end moments. Then write the joint equilibrium equations. Then solve the joint equilibrium equations to get the unknown rotations and deflections. Then substitute the value of unknown in slope deflection equation to determine the end moments. Then treating each member of a continuous beam as simply supported beam subjected to given loading and end moments, determine the end reactions. Then find out the shear force value at different positions. Then draw the shear force diagram and bending moment diagram. So these are the steps used for the analysis of continuous beam or rigid frame. Then coming to what is the expressions for finding the fixed moments for different loading conditions. If the concentrated load is present at the midpoint of the fixed beam, then you know the piston moment that you can find out at the end of the member. So here at the end B, the moment MFBA is equal to plus WL by 8. As you know, the clockwise moment is positive and the anti-clockwise moment is negative. So at the end A, so this is anti-clockwise direction. So the piston moment MFAP is equal to minus WL by 8. Similarly, this is the fixed beam, and here this is the loading W that is present at a distance small a from the support A and small b from the support B, and the length of the beam is L. So here at the end A, the piston moment is equal to minus WAB square by L square, as the direction of the moment is anti-clockwise, and at end B, the piston moments MFBI is equal to plus WA square B by L square, as the moment direction is clockwise. If the UDL present throughout the span of a fixed beam AB, so the moment at the end of the member MFAB is equal to minus WL square by 12 and MFBA is equal to plus WL square by 12. Similarly, for the triangular loading, if the intensity of load at end A is W and at B 0. So here the piston moment at end A MFAB is equal to minus WL square by 20 and MFBA is equal to plus WL square by 30. If the triangular load is present and the intensity of load is maximum at the midpoint W and at the end A and B 0. So this case, the piston moment at the end A minus 5 by 96 WL square, and the piston moment at the end B, MFBA is equal to plus 5 by 96 WL square. Similarly, if the moment is present at a distance small a from the support A and small b from the support B, and the moment that is M. So due to this effect of moment, the end moments that you can find out, the end piston moments at end A, MFAB is equal to minus M by L square B into B minus 2A, and at the end B, the moment MFB is equal to minus M by L square A into 2B minus A. Both are anti-clockwise, so negative. Both the moments are negative. Similarly, if the clockwise moment is present at the midpoint of the fixed beam, so due to this clockwise moment, the piston moments which is generated at the end of the member, MFAB is equal to plus M by 4, and at the end B, MFBA is equal to plus M by 4. The moment produced at the end of the member is clockwise, that is positive value. So these are the different piston moments for different loading conditions. Then what is the force and displacement relationship? Already I explained here. So due to the rotational displacement, let theta be clockwise rotation at A and end be considered fixed, and due to this rotational displacement theta A, the moment caused by rotation theta A at A 4EI theta A by L, that is 4E K theta A. K is the relative stiffness of the member, so K is equal to I by L. Similarly, the moment caused by rotation theta A at B, that is 2EI theta A by L, so this is equal to 2E K theta A. So this is the moment caused by rotation theta A at A and B. This is at A and this is at B. So these moments are taken as the positive due to the clockwise nature. The positive rotation at A causes positive moment, and negative rotation at A causes negative moment. Similarly, let theta B be the, this is the theta B, be clockwise rotation at B, and end A is fixed. So the moment caused by rotation theta B at B, this side, the moment that is 4E K theta B, that is 4EI theta B by L, that is equal to 4E K theta B. The moment caused by rotation theta B at A is equal to 2EI theta B by L is equal to 2E K theta B. These moments are clockwise and hence positive. The positive rotation at B causes positive moment, and negative rotation at B causes negative moment. Then due to the vertical displacement, so let delta be the vertical displacement of B with respect to A. So here the moment at end A and B are minus 6EI delta by L square. So this is considered the positive displacement. So for this positive displacement, so this is the moment induced, that is minus 6EI delta by L square. As you know, I by L is equal to K, so minus 6E K delta by L. So this is the moment at the end A and B due to the translation displacement. After superposing all the four conditions, the total moments MAB and MBA will be moment MAB is equal to 4EI theta by L plus 2EI theta B by L minus 6EI delta by L square plus MFAB. So you know I by L is equal to K. So MAB is equal to 4E K theta A plus 2E K theta B minus 6E K delta by L plus MFAB. Then after simplification, MAB is equal to 2E K 2 theta A plus theta B minus 3 delta by L plus MFAB. Similarly, the moment MBA can be determined. This is due to the rotational displacement at B, 4EI theta B by L. This is due to the rotational displacement at A, 2EI theta A by L. And this is due to the translation vertical displacement minus 6EI delta by L square. And this is due to the transverse loading piston moments, that is MFBA. MBA is equal to 4EI theta B by L plus 2EI theta A by L minus 6EI delta by L square plus MFBA. Then after simplification, MBA is equal to 2ek 2 theta b plus theta a minus 3 delta by L plus MFBA. So already you know the final moment and the displacement relation. Then coming, what are the different equilibrium equations of a continuous beam for different end conditions? Look at this figure. So here the both ends are simply supported. This is 3-span continuous beam with the support A and support D is simply supported, and support B and C is the intermediate support. I1 L1 is the moment of inertia of the span AB and the length of the span AB, and I2 L2 is the moment of inertia of span BC and length of the span BC, and I3 L3 is the moment of inertia of span CD and length of span CD. So these are the rotation at A theta A, at B theta B, at C theta C, and at D theta D. So here there are 4 rotations. So you need 4 equations to get the unknown displacement component. Here all the supports are at the same level, so there is no translation displacement express. So only you have to consider these 4 rotational displacement are the unknown quantity. So that you can find out by taking the 4 equilibrium equations. The first equilibrium equations you get at the joint A, at support A, that is the summation of moment at A is equal to 0. That is MAB is equal to 0. Then the second equilibrium equation you get at joint B. So the summation of moment at B is equal to 0. So here MBA plus MBC is equal to 0. Then the third equation you get at joint C, that is the summation of moment at C is equal to 0. That is MCB plus MCD is equal to 0. And the fourth equilibrium equations you get at joint D, that is the summation of moment at D is equal to 0. That is equal to MDC is equal to 0. So by using these 4 equilibrium equations, you can find out these 4 unknown displacement. If the ends A and D are simply supported, the moments at the end A and D will be 0, because here the moment 0 and here also the moment 0 due to simply supported end. So MAB MDC is equal to 0, and the another 2 equilibrium equation, that is at B and C joint, at B and C joint. So at B joint MBA plus MBC is equal to 0, and at joint C MCB plus MCD is equal to 0. So these are the 4 equations. So by using these 4 equations you can find out the 4 unknown displacement. With the help of these 4 equations, 4 unknown theta A, theta B, theta C and theta D can be determined. Then the moments can be found out. Then look at this figure. So this is 3-span continuous beam. So here the support A is fixed and the support D is simply supported, and support BC is the intermediate support. So due to the fixed end at A, here the slope is 0. If you draw a tangent to the elastic curve, the tangent will pass through the axis of the beam, so there is no slope or there is no rotational displacement at A. Theta is equal to 0. Only you get the rotational displacement at B, C and D. So there are 3 rotational displacement, theta B, theta C and theta D. Theta is equal to 0. So here you need 3 equilibrium equations so that you can find out the unknown displacement components, theta B, theta C and theta D. So here you take one equilibrium equations at joint B, that is the summation of moment at B is equal to 0, MBA plus MBC is equal to 0. Then the second equation, that is the summation of moment at C is equal to 0, that is MCB plus MCD is equal to 0. Then the third equation, that is the moment at D is equal to 0, that is MDC is equal to 0. This is due to the simply supported end. By using these 3 equilibrium equations, so you can find out the unknown displacement theta B, theta C and theta D. 3 equations are MDC is equal to 0, sum of moments at C is equal to 0, MCB plus MCD is 0, sum of moments at B is 0, MBA plus MBC is 0. So with the help of these 3 equations, 3 unknown theta B, theta C and theta D can be solved, then the moments can be determined. Look at this figure. So here the support A and support D both are fixed, and B and C are the intermediate supports. At A, so due to the fixed end, so here the slope or the rotational displacement, that is theta A is equal to 0. Similarly at support D, due to fixed end, the rotational displacement theta D is equal to 0. And here you get the rotational displacement at B and C, theta B and theta C. In this case, so you need two equilibrium equations so that you can find out the two unknown displacement, theta B and theta C. So here you take the first equilibrium equations at joint B, that is summation of moment at B is equal to 0, MBA plus MBC is equal to 0, and the second equation that you get, summation of moment at C is equal to 0, that is MCB plus MCD is equal to 0. By using these two equations, you can find out the unknown displacement theta B and theta C. Two equations are sum of moments at B is 0, that is MBA plus MBC is equal to 0, and sum of moments at C is 0, that is MCB plus MCD is equal to 0. So with the help of these two equations, the two unknowns theta B, theta C can be determined. Then you can find out the final moment by using the displacement. Now you are clear what is slope deflection equations and what are the assumptions, and what are the sign conventions, and the derivation of the slope deflection equations, then application of slope deflection equations, then the steps used for the analysis of continuous beam or rigid frames, then the expressions for finding the piston moments for different loading conditions, then the equilibrium equations of a continuous beam for different end conditions.